These are the notes for the first part of Chapter 5. 5.1 Day 1 was just a review of pre-calculus, so I am not going to videotape that. So what we're going to be doing in most of Chapter 5 is working with some derivatives and integrals in regards to both e and ln. So recall the power rule for integration and what its antiderivative is, that when we do the antiderivative of x to the n with respect to x, remember our antiderivative power rule says you add 1 and then divide by that power, and we've been using that a ton, and then of course we've got Carl on the end of it. But if you kind of look, we've never integrated when n is a -1. And keep in mind why. It's because if we do that, we end up dividing by 0. So when n is equal to -1, we don't have a power rule, which means we don't know what the antiderivative is of x to the -1, or equivalently written as 1 over x dx. And this is a very big question for us. But before we tackle it, what we're going to do is look at a calculus derivative. Because integration is the inverse of derivation, if we can figure out the derivative of what is equal to 1 over x, well then we could figure out the antiderivative of 1 over x. So basically what I'm going to be doing is taking a little investigative approach here on the calculator. So we're going to kind of investigate what is the derivative with respect to x of the natural log function. And we're going to do that investigatively here. We're not going to do a proof. We're just going to go to our calculator, and what we're going to do is in y1, we are going to put our derivative. And remember how we do that. We choose Math 8. And so I'll go back on my calculator here. These are the directions for the TI-83 and the Inspire, but I would like to apply that on my TI-84. So what I'm going to do is go to my y equals button, clear this off, and clear off my old garbage here. And I am going to have my calculator take the derivative, which is a Math 8 option, of the natural log function. Whoops. Let's see if that'll... Why is that not doing dx? There we go. And I'm going to do ln x, and I'm going to run that from x to x. And then what I'm going to do is go look at my table, and I'm going to see what happens here at 1, at 2, and 3, and 4. Keep in mind what my y1 is graphing is the derivative with respect to x of the natural log function at each one of these numerical values. So the derivative of ln1 is 1. The derivative of ln2 is a half. And at 3, it's 1/3. And at 4, 1/4, and then 1/5, and then 1/6. Those are the decimal equivalents for those fractions. So going back over to my table here and filling it in, what I have was that the derivative was 1, 1/2 or 0.5, 1/3, 1/4, 1/5, 1/6, 1/7. I probably have too big of a chart here. I don't really need to be this specific. But in general, x, 1 over x. So kind of interesting that when we take the derivative with respect to x of the natural log function, we get 1 over x, or we get its reciprocal. So that's the relationship I'm noticing. So what that gives us is a first really important derivative when we're dealing with e's and with natural logs. And it is basically what I just told you, that the derivative of the natural log of x is equal to 1 over x. Keep in mind we need to have x greater than 0 because we can't natural log negative numbers. And then equivalently, we have a chain rule application that says the derivative of the natural log of u is 1 over u times the derivative of u. And remember, this is where u is some function of x. So let me show you what this means. If I'm just going like this, the derivative with respect to x of the natural log of x, I get 1 over x. If I were doing the derivative with respect to x of the natural log of, say, sine x, Well, this is a function of x. So I do 1 over u, which would be 1 over sine x, times the derivative of u with respect to x. And the derivative of sine is cosine. Equivalently, this would give me cosine x over sine x, or cotangent x. So basically, you just do 1 over u du dx. Or you can even think of it as u prime over u, because that's basically what I'm getting right here is u prime is cosine over u. I like the 1 over u du dx, though. I think that's a little easier to understand. So what we have is something that actually you really do need to memorize. You need to get it in your head that the derivative of the natural log function is 1 over x. And this can be written several ways. We could say if y is equal to ln x, then we could say y prime is 1 over x. Or if y is equal to ln x, then we say dy dx in Leibniz notation is 1 over x. Or, if it was f of x is natural log of x, then f prime is 1 over x. This is all the same stuff. The power will come in the chain rule, that when we take the derivative of the natural log of any function of x, be it 8x plus 4, sine x, e to the x, whatever it is, where u is some function of x, we still do 1 over u, but then we multiply it by du dx. And this right here we can call u prime. So sometimes you'll see that written as u prime over u, or the derivative of the function over the function itself. And again, I've restated that here. You can see it's a pretty big rule, so we've got to get it down. What we're going to do is go practice it. It's very algebraic. You just have to watch the details. So the derivative of ln u is 1 over u times du dx. So this would be 2 over 2x, which is 1 over x. It's basically u prime over u. U prime over u. The next one, here's my u. My derivative is 1 over u times du dx. The derivative of x squared plus 1 with respect to x is just twice x. So this gives me twice x over x squared plus 1. Kind of easy peasy, right? You might say, where's Carl? Carl doesn't live in derivative world, kiddos. He's just there when we take an integral. So on the next one, now we're going to make sure we remember all our other rules while we're using this new rule. When I'm doing the derivative of a product, I use the product rule. It says I do first times the derivative of the second. Derivative of ln x is 1 over x, plus second times the derivative of the first. And the derivative of x is simply 1. So what this gives me is 1 plus the natural log of x, and I'm done. Nice, huh? So be careful with this next function, because this is a chain rule. I have an inner function of ln x and an outer function of cubing. So this is u cubed, which is 3u squared times the derivative of the guts. I'm going to use a little formal notation here. So this is a chain rule. 3 ln squared. Make sure you put it in parentheses, because ln x squared is different than ln x squared. What? You just said the same thing. No, I didn't. You just can't see the parentheses in my voice. The derivative of ln x is 1 over x, and it puts that on the bottom. Now, I kind of glossed over what I just said, but it's important, and it requires an e. The derivative with respect to x, if I had written it like this, is much different, because on this one, this is ln of u. So this is 1 over u times du dx, or equivalently, u prime, 3x squared, over u, x cubed, which is just going to give me 3 over x. So just nice, easy application of our newest derivative rule for the natural log function. Now, because we're going to be working with the natural log function, we've got our properties that are going to help us split things up and make them easier to integrate. The first being, let's go over here, that ln of a times b can get expanded into ln a plus ln b. The second is ln of a divided by b, and we're only concerned about the expansion of the logs, not the condensation of the logs, because if they get condensation, they get damp, they get moldy, we get black lung. It's just not good. So the next one is ln of b to some power. The power comes out front, and we are going to use those all in conjunction with each other to help us find an antiderivative. So for this one, f of x equals ln the square root of x plus 1, what I'm going to do is use my natural log property and write that as x plus 1 to the 1/2. And then I'm still, notice I'm not taking a derivative yet. I'm getting that power out of there, because although I could do this as u prime over u, it kind of makes an ugly derivative and an ugly chain rule, where now when I've used my power property for natural logs, what I really will have when I take the derivative here in red is the constants don't affect my derivative. The derivative of natural log of u is 1 over u times u prime, or du dx, which in this case is just 1. So it falls out nicely when I've used that, the rules for natural logs. They really do help clean things up. Now we're going to take a big jump and do one that's a lot more difficult. So look at this big ugly mess. If I were going to try to integrate this without using my natural log properties, I might go a little crazy. I'd have quotient rule up the yin-yang, and then I'd have a bunch of crud going on the top, and it just would not be fun. So I'm going to expand this using all my logarithm properties. First of all, it's a division problem. It's ln of a chunk over ln of a chunk, which means I'm going to write it first and foremost as subtraction. So I've got ln x times x squared plus 1 quantity squared. Subtraction expands into division expands into subtraction. Furthermore, that 1/2 power, or that square root, is coming out as a 1/2. Next, I've got a product here. Products expand into addition. Exponents come out front. So I'm going to combine two properties here in one. And same here, exponents come out front. So I'm using my properties of natural log expansion, and now once I've got it all expanded, now I'm ready to take f prime. The derivative with respect to x of ln x is 1 over x, plus 2 times 1 over u du dx, or u prime over u, minus 1/2 1 over u times du dx. And when I clean that all up nicely, I get 1 over x. I don't know why that became a multiplication, plus 4x over x squared plus 1 minus, these will cancel, 3x squared over 2x cubed minus 1. And you wouldn't be required to get a common denominator with that, because that would be cruel and unusual punishment. So because some functions do tend to go negative and we can't natural log negatives, sometimes you'll see the absolute value in here. But really what that means is we do it the same way. The problem is cosine in its domain can go negative, and we can only take the natural log of positive things. So when we're doing ln of cosine x, you'll notice what I get is same thing, u prime over u, or I like 1 over u du dx. So I would have, this is considered u, 1 over u times the derivative, back to a little formal notation, the derivative of cosine is negative sine, So you'll notice that what I have here is the derivative of ln of cosine x is negative tangent x. It's interesting because we haven't had an antiderivative for tangent yet. And what the antiderivative is for tangent, we haven't had one. We have one for cosine and sine, and we have one for secant squared, but we don't know the derivative of what is tangent is a question we have not yet answered. And now I know what it is. It's negative ln cosine x. Technically, plus a little Carl going in there, but that's a later date. I don't want to mess with your head here. So let's move right along here. Now this says bonus video, but it's not going to be. I'm going to expose you guys to this. I won't test you on this, but I do have it as an extra on your test and as an extra, I believe, on your first problem set. So I do want to go through this one. I believe it's worthy and I like it, and it helps in Calc 2 to be good at this stuff. So I'm going to teach you something called logarithmic differentiation. So although this expression up here for y doesn't have any natural logs in it, if I were to try to find what y prime is right now, it would just be a pain. I'd have to write that as x squared plus 1 over x squared minus 1 to the 1/3 power. I'd have to do 1/3 times that chunk to the negative 2/3. Then when I do the derivative of the guts, I've got quotient rule, and it's going to get messy. So as an aid in differentiation, sometimes what we'll do is we'll take the natural log of both sides so we can apply our logarithmic expansion rules to make it easier to work with. So I'm going to rewrite this function. And when we use logarithmic differentiation, what we'll do, we'll start off first by taking the ln of both sides. Because if I can take ln of the left and ln of the right, I'm going to write that like this. I like to see those powers when I'm doing this. Then what I can do over here on the right-hand side is use my properties for expansion, that the power comes out front and that division expands into subtraction. Now you got to be careful here because it's that whole chunk to the 1/3. So you've got to make sure you put that chunk when you expand it in a set of parentheses, or you will get the wrong answer. So this would be ln of x squared minus 1, all of it. And the reason that helps me is because once I take the ln of both sides and I kind of expand it all out, what I'm going to do next is take the derivative of both sides with respect to x, and I'm going to write that formally. So I'm going to do the derivative with respect to x of my natural log of y. That will equal, I'm going to pull that constant out front because I know that's not going to affect anything, but it'll be derivative with respect to x of natural log x squared plus 1 minus natural log x squared minus 1. Now what that allows me to do, the derivative with respect to x of the natural log of x is 1 over x. But when it's some function of x, like u, this is actually implicit because y is itself a function of x. So what we need to do is we need to say, well, that would be 1 over y times, normally it's du dx or u prime, but this is y prime, or dy dx. This is nice because this is what I'm ultimately trying to figure out, is what is the derivative. That should have actually said on the directions that I need to find y prime. I'm trying to differentiate here. So I'm going to erase that and write it a little nicer. What I've got is a gigantic eraser. I get 1 over y times dy dx is equal to 1/3 times the derivative with respect to x of ln x squared plus 1 is 1 over x squared plus 1 times du dx, or u prime over u. Same here, y prime over y. Minus, again, u prime over u is sometimes quicker if you get used to it. So when I clean this up, I've got y prime over y is equal to 1/3 of 2x over x squared plus 1 minus 2x over x squared minus 1. What that gives me, now it depends on, what kind of a problem you're doing, because technically I could now just say, well, if I multiply both sides by y, I have y prime. So I've got all this stuff I've already written. This is getting really analytical here, a lot of algebra manipulation. But there's this whole chunk, and what I'm going to do is multiply it by y. Well, what's y? It's way up on the top there. It is x squared plus 1 over x squared minus 1 to the 1/3 power. Looks like matrix notation, but now, technically that's the right answer. But for fun, wouldn't it just be a blast to clean that up? And I think it would be, and I'm dying to, so I'm going to. I'm going to go get a common denominator in here with my crisscross applesauce. It'd be 2x times x squared minus 1 minus 2x times x squared plus 1 all over apple sauce. All right, so that's cleaning that up. Let's just let this other one hang around in the shadows for a little bit. Now when I go clean all of this up, what do I get? I'm just doing this for fun. I don't even know if it's going to get much nicer, but I have a 2x cubed minus 2x minus 2x cubed minus 2x. So my x cubes are going to cancel. I do get a nice negative 4x on the top of that, which I do like a lot. So I've got a negative 4x over that product. That's pretty. And then I also have this x squared plus 1 right here to the 1/3 over x squared minus 1 to the 1/3. Now let's see what I can do here and see if it gets any better. I have this factor on the bottom and this factor on the top, and that's going to leave me with a 2/3. So let's write this. I've got the negative 4x on the top. I've got the 3. So I'm good, I'm good, I'm good, I'm good. Now I'm combining these like bases. This is really to the 1. So when I do 1/3 minus 1, I get negative 2/3, which is going to throw this one down here to the 2/3 power, I believe. And then I've also got on the bottom a multiplication of the same factor. When we multiply, we add exponents. So I get x squared minus 1 to the 4/3. Now, as much fun as I thought that was, it's probably legal for you to have left it right here, and you would be in my good graces. But this right here is just too much fun to deny. So that's the end, and the bookwork assignment's right down here. The key is posted on Edmodo, and you have a good one. Peace out, Girl Scout.